So today, I wanted to talk about, this is continuing on the theme of periodic systems and periodic motion. There's a couple of topics I wanted to get to. One of them is kind of this general framework. This will work for any vector field that is time periodic. So mechanical systems that have periodic driving forces are just a subset of this. But I thought I would start with this because this would be like the brute force computational thing you would do if you don't have anything else to do any analytical work with. As long as you know that your vector field is periodic, then you could use basically this method. So the setup, and you could do this in Rn, but let's first talk about R2, because R2 is where 1 degree of freedom mechanical systems will live. So that's a good place to start. Plus we can draw it and visualize it, but all of this extends to Rn. If you've got a first order vector field, most likely nonlinear, that's of this form. So x dot equals f of x, where x, we're considering 2D system. So x has components x1 and x2, and f is periodic in its time component, meaning this vector field f repeats after every time capital T. So then, and this is copied from last time. These are some snapshots of just some typical vector field that will repeat in time. The red is the vector field. We're looking at time slices, sometimes called snapshots, at different points in time. If you started with some initial condition like this x over here in the lower left, and you follow it through time, it's going to kind of trace something out in this space-time diagram. And once it reaches this edge over here, little t equals capital T, well, now the phase is back to the beginning. So this upper point up here, highlighted in yellow, basically starts back at the beginning of this cyclical time, because all that really matters is the phase. We start back at the beginning, and then this continues on and maybe does some things, pierces surface in various places, and then this goes on and on and on. So this would be x after 2t, and it would just kind of go on. So you could look at, you could view the evolution of all possible initial conditions in this setting where we identify time 0 and time capital T, the period. So all that really matters is the phase that we're in. So the time becomes a cyclical variable rather than stretching on to infinity in both directions. Actually, time ends up living on, if you think of the phase of the forcing, then that lives on the circle. So it's kind of hard for us to picture, but if you were to, and this is what's commonly done, is we consider the Poincare map, which is just taking initial conditions at some initial time and following them forward. Where do they map to after one period? And then you kind of take these snapshots. Instead of having to worry about the snapshots, you're just looking at what happens to individual points as they evolve discretely in this map. So this is sometimes called the time T map or the stroboscopic map, because it's like you're strobing the system at every period, like a big strobe light. Sometimes this is done in physics experiments. You literally put a strobe light. But here we're strobing the phase space. So here's some initial condition x. Here's where it maps to, this time T Poincare map. And that's why we call it P. So after one iterate, we say of the map, that's where we are, P of x, then maybe after 2 iterates, we're here, etc. So so it's a useful idea. The phase space becomes, we call it the extended phase space. Let's say x1, x2, and we can either call it time or theta. So then we've got, this exists in R cross S1. What is theta? Well, if the period we could write it in terms of a frequency. So the period capital T is 2 pi over omega. Omega is in radians per second. If we use this as our time variable, so we're using the phase, then theta dot is just omega, and we kind of add this to, there's going to be x1 dot is whatever that first component of that vector is, x2 dot is whatever the second component of that vector field is, and then this time direction, omega is a constant, it's positive, so the vector component that's kind of pointing in the time direction is always the same magnitude wherever you are, and it's just taking you in the direction of time. So we take our 2D time dependent vector field, which was x dot as f of x and t, and turn it into a 3D, in some sense, time independent vector field, which is easier to analyze. So let me describe some simple behaviors that can happen, and then we'll look at that numerical example that I'll put into the Google Drive if I haven't already. So here's some simple behaviors. These are possible solutions, just to give you the idea of what kind of behaviors can happen in a system like this. I'll just do my little schematic of, here's that time variable, or equally the phase. If I have some initial condition here, and it evolves, I don't know what it does, but as long as it comes back to its same location, P of X. So if P of X equals X for some X, then X is an initial condition. Let me just put IC, an initial condition on a periodic orbit of period T, capital T. That doesn't mean that every initial condition is a periodic orbit. I could do some nearby initial condition, and maybe this, goes over here. So that means it's down here, and I don't know, it does some other stuff, but it's not periodic. So this is a period T, which would be the minimal period you need. You can't have any solution that has a period less than T unless it's something trivial, like it's just a straight line, it doesn't do anything. That would be like an equilibrium point. But you could also have solutions that repeat, because remember this side and this side are kind of matching in time. If I've got an initial condition and it goes somewhere like here, and this one goes up here, and that point goes back to the original point. It goes down and then up. So if this is X, and wait, so let me keep track of this. This is P of X down here. So this is P of X. P of X maps to twice the application of P, so that's P2X. Here's P2X. And that goes to P3X. If P3X equals X for some X, then X is an initial condition on a periodic orbit of period 3T. So you could have things like that going on. You can even have quasi-periodic behavior, which would be So quasi-periodic behavior would be if I see that my initial condition, maps to here, and then it maps, I don't know, here, and then it maps. I'm just going to be mapping. They kind of map around and seem to be filling a closed curve. Well, in the extended phase space, there may actually be a closed curve, and things are just sort of, all these trajectories are kind of crawling around on them. So because you can identify, right, we identify this side with this side, this thing that appears to be a closed curve really does have the topology of a torus. So if an initial condition X seems to trace out a closed curve in the map, right? That means that if we're looking just in the X directions, this thing seems to trace out a closed curve. And it's very likely that in this extended phase space, we have a torus. We've got quasi-periodic motion. As we'll call that as a quasi-periodic. It's an initial condition on a quasi-periodic orbit or torus, right? Since we can identify these two, we can glue the two sides together. We've got a torus, two torus. So that kind of stuff can happen. You could also have just purely chaotic motion. Purely chaotic motion isn't going to be any one of these. It won't, if an initial condition is chaotic, it won't ever come back to the same point. Because if it did, it would be periodic, even of some large period. Chaotic motion is not periodic. So if you have an initial condition that never repeats, it'll seem to fill an area, typically, fill a region and look kind of messed up. So if you have some initial condition and it's not going on what appears to be a closed curve, it seems to be filling an area, then that's qualitative evidence that it's chaotic. So if the mapping of an initial condition X seems to fill an area, and it's chaotic trajectory. And in mechanical systems, it's often the case you'll have all these different types of things all existing, meaning there'll be some regions of initial conditions that lead to chaos, some regions that are periodic, and some regions that are quasi-periodic. There's some constraints on what type of motion can happen depending on the structure of the vector field. So if the Poincare map comes from a Hamiltonian system, I guess if we could say it comes from the flow map of a Hamiltonian vector field, then the Poincare map is area preserving. So if you start with small regions of area, they will be preserved. So if I have a, this isn't a property of individual trajectories. It's actually a property of ensembles of trajectories. So instead of looking at a single trajectory X, we're looking at a region. So if a region R, we look at how it maps right? And we can define the Poincare map of an entire region. It's just the Poincare map of all of the individual points, but the area of that region stays the same. That's if we've got a Hamiltonian vector field. In general, we won't have a Hamiltonian vector field. So in general, area is not preserved. If my system, let's say it's a mechanical system with dissipation added, or I don't know, it came from some completely different realm of applied math altogether. Maybe a model of epidemiology and outbreaks. Then there's no constraints from mechanics. And our initial region R, if you look at successive iterates of it, maybe it starts shrinking and shrinking. So here's like P2 of R. Maybe it shrinks down to a point. It actually doesn't have to. Something that has no area isn't necessarily a point, right? A curve has no area. So there's other things can happen. So everything might shrink to a point. Which, by the way, if it's shrinking down to a point, this point keeps mapping across. What we actually have is things mapping down to a periodic orbit, shrinking down to a point in the map. Therefore, a periodic orbit in the continuous system. Right, the Poincare map, there's some savings because you get to analyze a continuous system just by taking a slice and looking at mappings. So there's some dimensionality savings, but you always need to have those two interpretations in mind. So if a region shrinks down to a point, well, that point keeps mapping back to itself. So you've got a periodic orbit. Other things can happen.
A quick question about that.
Yeah, go ahead.
So does that mean that the region that is shrinking down to the periodic orbit is a stable manifold to that periodic orbit?
Yes, but it might be like it might be global. So the entire phase space maps to that point, in which case you haven't gained anything because the whole phase space is the stable manifold.
I see, okay.
It gets interesting if there's some subset and, along that things will map to the periodic orbit, and in other directions they won't.
Right. Okay.
Yeah.
Thank you.
So there's other things that can happen. You can get strange attractors, which means if you started with some region, it will, over usually a long period of time, map to some kind of weird curved thing that has no area. So let's just say this is P of N of R as N goes to infinity. It has no area, but it could be infinite. So if something has no area and is infinite, now we're getting into geometric things called attractors. In fact, these are called strange attractors. And in mechanical systems, they show up as if you have a combination of damping and forcing, you can see this kind of behavior. This also is an attractor. Here, the left case, here the attractor is just a point, so it's not terribly exciting. Whereas this one could be more interesting. So strange attractors can happen. And a system that's been studied quite a bit is and I guess it was initially studied by Duffing, the Duffing equation. So you could think of this as it's a second order ODE that we could write in first order form, but we either have plus or minus Q, and then a cubic term, and maybe some damping. Let's put some damping in there. And then usually some kind of forcing. So here's kind of the full-blown Duffing equation. Plus Q for this means that you've got a stable origin, and minus Q for an unstable origin. If you want to think of it in terms of a potential energy, here's potential energy. Plus Q means that the origin is the valley of the potential energy, and minus Q makes this into the top of a potential energy. We usually think of the magnitude of epsilon is small. And so this equation describes a few different things. I think I've got a video of one. We took we made a track for a ball, just a one-dimensional track, kind of like a roller coaster. And that was the track. So you could look at this as the coordinate Q, and this is the case of the unstable origin. So the ball moves. There's natural damping, either due to air resistance or the friction with the track. And then we were shaking this. We attached this to some kind of shaker. And I have a movie of it. I actually gave it away, but it was in my lab for a while. So it's a monstrous thing, kind of frightening. I have it here. Let's see if this works. It's kind of a big video. I hope it's not too loud because you can hear the gears and it's kind of whiny. So that's the device. This black thing is the track that we made. We're shaking this from the right with about 1 Hertz frequency. And the ball that's on there, think of the size of a marble, or in olden times, before people just used trackpads, there were mice, these little mice things that you'd use for your computer, and they would be, it was like a metal ball that had a rubberized outer coating. We had a hard time finding them because they don't make mice anymore, but it's good for rolling on this little track. I think I've even brought this track in. I just haven't. Okay, good. I don't hear any sound, so the sound's not important, but you can kind of see we're shaking this back and forth, and it's doing some interesting things. If we strobed this, so looked at the Q and Q dot every period, we would actually see some kind of chaotic looking motion. And you might wonder, well, does it ever go off the sides? Yeah, the video ends when it goes off the sides. I guess I can just show it. Like, yeah, okay, so experiment's over. But other people have looked at similar things. I have a friend at Duke who it's an experimental mimicry of Duffing's equation. And look, this is 1992. That's ancient history. None of you were probably even born then. Yeah, some stuff about the governing equations. I put all this in the Google Drive, I think, too. So they did it fancier, but I wasn't looking for fancy. I was just looking to have something cool to show. We were going to do some experiments with that, but other things got in the way. I just want to see, they did some careful collection of data where they can see things like this happening. This is settling down into one of the wells, I think without any shaking. And we were able to actually duplicate that. And then where's the vibration results? They vibrate and they just kind of go on and on. Yeah, so here's kind of a typical trajectory that you might see for the little ball moving on the cart. And I think that they're trying to minimize friction, but friction is still present. This is just a trace of what it does in terms of cart position and cart velocity, or ball position and ball velocity. If you do the careful mapping every period of your forcing, and collect, in this case, 10,000 points. So look at 10,000 periods. You could see this interesting pattern. This is what they believe to be a strange attractor for the system. And this is it. This is looking at different phases of the strange attractor experimentally. And you can peruse that. Let's see if this GIF works. Yeah, okay, cool, it does. So this is kind of showing strange attractor. Here's the initial condition kind of weaving through it. So on this schematic, we've got the position and the velocity, and then the azimuthal coordinate going around. That's the phase of the forcing. So we're only plotting at the same phase. I think you could also view, if we were to follow that surface around through phase, you'll see this thing, and we're not showing the time here, but this does repeat. It repeats periodically. So it looks like stretching and folding back onto itself and doing this interesting repeating pattern. So that's a strange attractor. So that means it's an attractor. You start with any initial condition. It will eventually converge onto this object, which exists in the extended phase space. So you could have a guarantee that you'll be somewhere along this thing, but this thing is a fractal, so it has infinite length. And it was interesting to the experimental mechanics community when they saw that they could do that. So in the folder that I will provide, there is this thing called Duffing Poincare MATLAB, and I've provided some code. The main thing to run, just to see something, and it works for MATLAB 20. I think it works for earlier versions. I think this was designed for MATLAB 2015, so it should work. The main thing to run is run me Duffing, and that will produce a picture like this, which shows X and Y and some other stuff. I don't want to mark this up. It shows some background points, which started from, it was like a grid of about 20 points, and they were followed either 100 or 200 times. And then it shows kind of this background, these background points. You see things that look like closed curves. So those are the quasi-periodic orbits. You see where these closed curves are kind of shrinking down to a point, and those would be stable periodic orbits. And there's this chaotic C, this thing that looks like a bunch of scatter shot, seems to fill an area. It's chaotic, but also within that is an unstable periodic orbit. And so one of the things that I asked you to do for homework problem 1 is find the unstable periodic orbit for that other system, the one related to a boat being forced under roll. Let's say I'm going to try to share my screen, another screen, see if I could do it. It's not letting me. How do I share my screen? Can I override? Yes, I will do this. Oh boy. Okay, it's showing my desktop. And I don't want to see this. Yeah, this was just the result of running code in MATLAB. If you could see the code. I just did run me Duffing. This other command just makes the fonts big. What I wanted to plot here would be the initial points that were followed around. And then I'll plot them as magenta stars. There we go. So hopefully you saw some magenta stars show up. Each of those, it's about 20 points, were followed 100 times and left a little gray dot. So this shows you kind of, I think I call this getting the lay of the land, like what are the possible behaviors that are there. And then what I'm showing, what this program Run Me Duffing also does, if I can zoom in, I don't know if I can. There's a circle, this tiny circle, it's near the origin. And that circle is maybe about 10,000 initial conditions. I forget exactly. And those 10,000 initial conditions are followed forward and backward, and they create these red and blue closed curves. I'm trying to zoom, and it's just not letting me. I don't know why. There's like the zoom stuff. Just zoom already. Yeah, I don't want property inspector. Maybe if I do the old-fashioned way. Nope. They might have trouble because of Zoom being on. But I'll show you a schematic of that. Let me bring up my other desktop again. Okay. Hopefully we're back. All right. Let me insert that picture. So this is from running that runme file, and you can adapt it, I believe, to show what you want, or adapt it by changing the ODEs. One of the functions in there is an ODE. You should see what's called, I think it's called Duffing, but this gets you pretty far along in doing that homework assignment. So yeah, we see, what do we see here? We see some quasi-periodic, region of quasi-periodic motion here. And then there's another region. Since I didn't have a bunch of initial conditions in there, you don't quite see it, but this is another region of quasi-periodic motion in light blue. And so what's separating the light blue and the light yellow is this chaotic C. There's even, it looks like there's probably some kind of boundary curve, like a torus that surrounds the entire part of the phase space that's shown here. And then you might be wondering, like, well, what's this little circle thing, and why are we doing that? What's the big deal? Well, the goal there is to find, there's in the chaotic C, there are unstable periodic orbits. So this is the chaotic, it's a chaotic region. Because it's metaphorical and pretty, I like to call it the chaotic C. And then there's these islands of stability, right? Islands of stability. But within the chaotic C, there are some periodic orbits. It's just they're hard to see because you don't in these islands of stability. Usually, you have things shrinking down to what would be in the middle, a periodic orbit in the middle, like in the middle of a target. So how do we find periodic orbits in the chaotic C? It's hard. I'll tell you that. You need to have a good guess of where they are, and that's what this little circle is. So if you have a guess, you can find them. If you have a guess, then, so let's say we have a circle, and this is a circle of initial conditions. We think are, it necessarily has to be unstable because it's in the chaotic C. Our unstable periodic orbit is in this circle. So maybe you choose a really big circle, I don't know. And then what you do, so we'll call this circle C. You follow it, you take that set of points that make up your circle and you iterate it forward under the Poincare map. And in this case, this is a Hamiltonian system. It doesn't have dissipation added yet. So the area enclosed by the circle must be the same as the area enclosed by the iterate of the circle. And you could just numerically verify that using Green's theorem. In fact, I think that's also in the program I give you. I mean, it's approximately equal because there's some numerical error, right? These are made up of, what I'm calling the circle is actually made up of maybe 1,000 initial conditions. And the main error comes from, right, when we take these initial conditions and follow them forward, there are places where two nearby initial conditions do a lot of stretching. And so the approximation of our curve is not very good there. So that would be following the circle forward. So if there is a periodic orbit, it has to be somewhere in the intersection of the interior of the circle and its first iterate, because otherwise we wouldn't have something periodic. But here's something else you could do. You could take that same circle and follow it backward. This would be akin to, we could write it as P inverse C. This would be from integrating time backward. And MATLAB has the functionality, you could just sort of set a final time that's negative and it'll do this for you. So this now constrains things further. If there is a periodic orbit, it has to be in the intersection of all three of these things. And then you could repeat this. You could say, okay, instead of starting with a circle, I'll start with this little diamond and repeat the process. Maybe I'll make the diamond purple. It's easier to see. So repeat process with the intersection diamond. And you can get as close as you want through this iterative procedure to a periodic orbit. Now, what kind of periodic orbit is this? It's a periodic orbit that has both a unstable and a stable direction. And those are nicely captured by, right, going forward, things are going to stretch along the unstable direction. And going backward, things will stretch in backward time along the stable direction. So if this is our, let's call this point P0 is an actual periodic orbit. This is this is a branch of the unstable manifold of that. And this is a branch of the stable manifold of the periodic orbit. And typically their periodic orbits are very unstable. How do I measure that? Because you can measure, if I had 2 points, how much does the distance between them grow? So if this was D0, then D after one iterate is going to be D0 raised to the, well, not raised, hold on. It'll be multiplied by some factor, lambda max, D0. This lambda max, this is the largest eigenvalue of the, right, because this is a periodic point, we could numerically construct that M matrix, the one that we've talked about before, the monodromy matrix. This is a 2x2 matrix. The M matrix, which is describing the linearized dynamics near that equilibrium point, P0. Okay, so you can follow this procedure and at least put constraints on where the periodic orbit is. It's kind of done for you for this Duffing example. I want you to do it for the homework 1 problem of the boat with roll being forced by waves. Now, if we add damping to this is the Duffing system, but with damping turned off. If we do add in damping, then we get all of those things that I was talking about. We get, I think I have it in here in the write-up. You could read this thing called Duffing Map Tutorial. It basically says what that software is doing. It also has another kind of physical motivation. This was some work done in the 1970s. They had a beam that at the end of it was, there was a magnet attracted to two magnets, and so the downward position was unstable. It wants to kind of be leaning towards one magnet or the other. In fact, I have one of these in my lab, and then you shake the frame. There's kind of built-in damping, which you could assume is linearized damping, because what else are you going to do? Stop it with the writing. There we go. This kind of walks you through how what we're getting here. And then if you turn on damping, so in this case, it's delta of 0.2, something small, and then follow that grid of initial conditions for a long enough time, but don't save intermediate points, only save like the last few iterates, then you'll get something that looks like this strange attractor. So this is the strange attractor for the Duffing system. The strange attractor that you get for the boat problem is slightly different, but it's the same sort of thing. Its phase space is shrinking down to something of zero area, but of infinite length, and that is a fractal. I guess you could, if you want to study more about the fractal nature of it. But anyway, that is that.
What topological dimension do those sorts of attractors have?
Yeah, so yeah, people have come up for fractals. They've come up with measures of dimension between that aren't whole numbers. So I don't actually know, but I think it's somewhere between 1 and 2, because it's almost like a space filling curve.
Oh no, I meant I misspoke. I meant topological composition.
Oh, like what are they? Do they fold back on themselves? Are they S1?
Or
I don't know.
Okay.
Are there any other questions about that? I'm going to go on to an analytical approach next for approximating periodic motion. Nope. Okay. It's still motivated by the Duffing system. The stable one, though. And this is Lindstedt-Poincare, something else Poincare did. It's called Lindstedt-Poincare perturbation theory. And this is a method for finding periodic orbits or approximating them. And I mean, if the world was linear, this would be easy, but this is approximating periodic orbits for nonlinear systems, which means systems with nonlinear terms. For those of you who are interested in orbital mechanics, this gets used in orbital mechanics quite a bit if you want to include nonlinear effects. A reference for this, I've given you the Hand and Finch, but this is in Hand and Finch section 10.3. So their chapter 10 is very good. So this can apply to a bunch of different systems. In the orbital mechanics context, this was used to find approximations to three-dimensional halo orbits around Lagrange points. But for describing the method, it's good to start with a simple example. So a classic example is the Duffing system. I guess we'll say classic simple example. And you could view it as a modified harmonic oscillator. At least for taking one of those sign choices so that the origin is stable. It's a modified harmonic oscillator with a cubic term. and studied by Duffing. So this is what I had before, but removing some terms. We're getting rid of damping. And we're getting rid of forcing, just to start out. And we're assuming that this nonlinear term, its magnitude, represented by the coefficient epsilon, is small. So this is the Duffing system. There is some ambiguity because of whether or not it's a stable origin or unstable. So I'll say the Duffing system with a stable origin. So there it is. And you might wonder, well, what kind of system can be put into this form? We've mentioned a couple. Another one, our old favorite, the pendulum, can be put into this form to leading order in the nonlinear term. So that's worth mentioning. So the pendulum can be put in this form. So if we're writing the pendulum equation as we're looking at a rescaled time so that our equation is nice and simple, theta double dot plus sine theta equals 0. Then we do the Taylor series expansion for sine theta. And this is theta minus 1/6 theta cubic, and then plus other terms that are of order 5 and higher. So that means we've got theta double dot plus theta minus 1/6 theta cubed is an approximation. So epsilon equals negative 1/6 for the pendulum. And we will come back to that. So you would use Lindstedt. Was there a question? Hold on. You would use Lindstedt-Poincare if you suspect that there are periodic orbits. So for example, this system, when epsilon is 0, so just this part equals 0, is the harmonic oscillator. So we know that that's got periodic orbits. In fact, everything is periodic orbits. And we suspect if we add epsilon q to the third power, where epsilon's small, we should still get periodic orbits. And you could numerically try that out. So you could just try looking at phase space if you want, and seeing that everything's closed for small enough epsilon. So when you suspect that there are periodic orbits, then you can try to write out what the solutions look like analytically. So the goal is analytical approximations of periodic orbits. So we want Q as a function of time written analytically. Like, yeah, we could do this numerically, try an initial condition and see it, but we want to get this analytically. So before we get to Lindstedt-Poincare perturbation theory, we want to talk about the usual perturbation theory. The usual perturbation theory is that you write this solution out by expanding in powers of epsilon. Starting with epsilon to the 0th power. So let's start out this way. If epsilon does equal 0, then we know that a solution is this, and we'll write it as Q naught T is A cosine T. This is a solution of, I guess I should give this a name. I'll call this equation star up here. It's a solution of star with initial conditions. And we'll keep using these initial conditions that Q is initially along, our initial condition is on the Q axis. So Q 0 is A, and then Q dot is 0. So in terms of the phase space, we're always starting over here, some distance A from the origin. And we think that this is going to do some kind of periodic motion. We don't know for sure, we hope. So for epsilon not equal to 0, we're going to look for solutions of the equation of motion of the following form. So Q is going to be a sum from n goes to 0 to infinity, epsilon raised to the nth power Q n t. Okay, so that's what we mean by expanding solution in powers of epsilon. So if we just write out the first few terms, which is useful. So we've got the 0th order term, epsilon times first order term, epsilon square, and so on. And if this converges well, then you could truncate this at a large enough epsilon and say, this is good enough. I've got a good solution. If we just substitute this assumed solution into the Duffing equation up there, the start equation, let's see what we get. And then equate terms of the same power of epsilon. Then the epsilon to the 0th terms will give us Q0 double dot plus Q0 plus epsilon raised to the first, Q1 double dot plus Q1 plus Q0. Right, because of that cubic term, things are going to get mixed up and thrown around. Epsilon squared, that set of terms is Q2 double dot plus Q2 plus 3 Q0 Q1 squared, and this just kind of goes on and on. All right, so that means we individually want to solve for, okay, this part equals 0, and then this part equals 0, and then this part equals 0, and so on. Okay. So for the first one, Q0 double dot plus Q0 equals 0. Well, we've already solved that. That's basically the unperturbed system. So if you solve for Q0 as a function of time with the given initial conditions, you get Q0, you get the same thing that we got before, A cosine T. Okay, no big deal. And now that gives us Q0T, right, which we can then plug into here, because now we have to solve at the next level. So this was kind of at the epsilon raised to the 0th. How about epsilon raised to the 1st? Now we need to solve this second order ODE. And I'll write it this way, minus Q0 raised to the 3rd power, which is minus a cubed cosine to the third power of time. We could use some trig identities and write what that is. Cosine 3t plus 3 cosine t. All right, now you could use your favorite method for solving Q1. Maybe you use the method of Laplace transforms. But since it's a linear ODE with some time varying coefficients, there's ways to solve this. So let's just say you solve for it. I mean, maybe you just plug it into Mathematica or whatever and let it do the method of Laplace transforms. Well, then you get a solution. And with the given initial conditions up here, with those given initial conditions, the solution is, it's gonna look nice. 1 over 32, a cubed cosine 3t minus cosine t. That looks fine, that's periodic. Oh, there's a problem. Get this other term, and it's got a t sine t. So whereas this part, this is periodic in time, so that's good. It doesn't grow or shrink, it's periodic. This is bad because of this t here. This term is going to grow without bound. And that's not very periodic. It's called a secular term in the literature. So that makes Q1T is not periodic in time. So that's a problem. If it had been periodic in time, then we would use this solution, right? And plugged it into here along with Q0, and then we'd solve for Q2 and so on in the chain of expansions. But we should just give up because, well, this solution is not periodic in time. However, if I plotted solutions of this ODE for those given initial conditions where A is some real number, you would see that it really does, things do loop back. It's periodic. So this approximation is getting things wrong. And that's what Lindstedt and Poincare addressed. What's the problem here? Well, the problem is that we're assuming the frequency is always going to be 2 pi. So the insight that Lindstedt and Poincare has is that they also changed the frequency. They treated the frequency as an expansion in epsilon. So they introduced the idea of also changing the frequency. And the naive way to do that would be as an expansion in epsilon. So here's what we do following their procedure. We introduce a new time scale that we'll call tau. And tau is going to be some frequency, omega, which will be a function of epsilon times t. And here's how we'll do it. So epsilon, sorry, omega is a function of epsilon. We'll just write it this way. It's going to be 1 plus epsilon omega 1 plus epsilon squared omega 2, and so on. Where these omega 1s and omega 2s could be functions of the initial conditions. So what this allows for is that different periodic orbits, especially think of this as different amplitudes, will have different frequencies as well, which we know for the pendulum. We know that small oscillations have a certain frequency. If you go to large amplitude oscillations, the frequency goes down because the period's going up. So you get to almost the inverted position, and it takes a very long time to do a whole periodic motion. So it makes sense to introduce this, that the frequency may be a function of amplitude. And that's what this allows for. So now we could expand, but using Q as a function of tau, not Q as a function of the original time. We're going to do Q as a function of this introduced timescale tau. So now we assume Q tau. This is all going to look the same as before, except where I replace T with tau. This is Q0 tau plus epsilon Q1 tau, epsilon squared Q2 tau, etc. All right, and now we need to plug this into the ODE. The ODE was written in terms of time, not this time scale tau, so we have to deal with that. The original ODE in terms of time, T, not tau. So that just means we've got a, right, okay, what is Q dot and what is Q double dot? So Q dot, this is dQ dt. Now using the chain rule, because we're going to be treating Q as a function of tau, this is dQ d tau d tau dt. What is d tau dt? From up here, it is omega. So this is dQ d tau times omega. And we'll just, for convenience, we'll use instead of over dot, we'll use prime and say that that means derivative with respect to tau. So it's Q prime times omega. And so similarly, Q double dot is Q prime prime omega squared. So the Duffing equation is now, we could write it in terms of tau. It's going to look like Q prime prime omega squared plus Q plus epsilon Q to the third equals 0. I get, maybe to emphasize that everything now is a function of tau, I'll just explicitly put in, we are looking for solutions of Q tau. And with the same initial conditions. So was that Q0 equals A, Q prime at 0 is 0. Okay, now we need to, generally what you do is you divide by omega squared. So that we'll have Q double prime plus some stuff. So we need to divide by omega squared. And what was omega written like there? So now it's useful to use a particular Taylor series. And hopefully you've seen this. you want to use this Taylor series, 1 plus delta raised to the n, where delta is small. This is 1 plus n times delta plus n times n minus 1 over 2 delta squared plus, and you can keep on going, like it's terms in third order and delta were larger. So this is a Taylor series expansion that you should memorize. It'll help you in life. All right, so then that means that 1 over omega squared is basically 1 plus epsilon omega 1 plus epsilon squared omega 2 plus dot 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 raised to the negative 2. Being careful, and so now this is in a form where it looks like that thing up there because all of this is delta. It's something small because we assumed epsilon small. You work this out, you get 1 minus 2 epsilon omega 1 minus 2 epsilon squared omega 2. You might, that's from the n delta part, but you can't forget this part with delta squared if you're going to do epsilon squared terms. And that gives us plus 3 epsilon squared omega 1. And let's just go that far. So that's everything up through second order and epsilon. Which might be overkill, but there it is. So now we've divided by omega squared, and what are we left with? We get q prime prime plus 1 minus 2 epsilon omega 1 plus, now let me group the epsilon squared terms. That gives me minus 2 omega 2 plus 3 omega 1, etc. This is all times q plus epsilon q raised to the third power equals 0. Right, that's what our ODE becomes. So you see we've got some additional terms. And so by some magic, things will work out. And I'll show you what the magic is. We're going to pick omega 1 so that that the Q1 part of the approximation is periodic. Okay, so now we substitute in, where is that substitution? We do this substitution. So wherever we have Q, we say that equals Q0 plus epsilon Q1 plus epsilon squared Q2, etc. You do that for the second derivative term and everything, and group by epsilon. What do you get? So here's the epsilon 0th, Q0 prime prime plus Q0. That's all you get there, plus epsilon Q1 prime prime plus Q1 plus Q0 raised to the third power. It's looking like we had before, but lo and behold, there's this new term that shows up. Ooh, that's new. Maybe that's going to save the day. Yes, it will save the day. Okay, then we got Q2 prime prime plus, you know, let's not even go there. That's thesis level. Okay, so like before, each of these individual powers of epsilon needs to equal 0. And so this first one is the easiest because now we've solved it twice before. So now solve for Q0 tau. It satisfies the initial conditions. And just notice this is periodic, okay? Because the cosine tau, there's no t or epsilon, e to the t or anything. So that's a periodic function, good. Now the next one, what do we got? Q1, so that was the epsilon raised to the 0th. How about epsilon raised to the 1st? Q, well, let me write it this way. I'll write it, this equals, and then minus Q0 raised to the third power plus 2 omega 1 Q0. And now we want to solve for a periodic Q1 tau. Okay. We'll do that by a good choice of omega 1. So we go through this, and what do we get? Let's write the right-hand side here. If we write the right-hand side, this equals 2a omega 1 minus 3/4 a cubed cosine tau minus 1/4 a cubed cosine 3 tau. It's maybe not clear yet, but it is this term which leads to that secular term from before. So if we want to get rid of this term, we pick omega 1 to make this term 0. And what does that give us? That leads to omega 1 is 3/8 a squared, by just making the parentheses term 0. Now the solution for Q1 tau is, it looks a lot like it did before, at least the periodic part. Cosine 3t, oh, sorry, tau. Gotta remember the tau, minus cosine tau. But there's no secular term, so that's it, which is periodic. Yay. So that means at least so Q tau equals Q0 tau plus epsilon Q1 tau is a periodic approximation. It's an approximation of a periodic solution with a frequency omega epsilon is 1 plus epsilon, and we got to put in what omega 1 is, 3/8 a squared. And in this case, we only went up to epsilon. You could do this up to any order you want. So if that's the frequency, so corresponding period is just 2 pi over that. I'm ending soon. T equals 2 pi over omega, which is 2 pi 1 minus epsilon omega 1 epsilon squared. Well, let's just leave it at that. Blah blah blah. There's other things. So for this problem, it's 1 minus 3/8 epsilon a squared. This is for Duffing, or at least this Duffing approximation. But remember, for the pendulum, which fit into this form, at least up through cubic order in the angle, epsilon is not minus 1/6. So T is 2 pi 1 plus 1/16 a squared, where a is the amplitude. So in the pendulum, if you start with some amplitude a, and this is going to go around, go back. It's periodic. The larger the amplitude, the larger the period. So here, let's just do a sketch of A versus the period. Here's 2 pi. And what this does is we've got this part that's quadratic in A. So this is going to go a little bit up, right? So larger amplitude, oscillations of the period, oscillations of the pendulum have a longer period. And what we expect is, right, as you get close to pi, I wrote the word pi. As you get close to pi, right, this period is going to go to infinity. It's going to shoot on up to infinity because the inverted pendulum has infinite period. So that's it. Took you a little bit over, but I think that's all right. Next time, we'll be looking at frequency response curves. So when you drive a system at a certain frequency, what kind of response do you get in terms of its behavior? We'll do that both for the linear case, then also the nonlinear case, which will be this Duffing oscillator, and with without damping. So we'll do that next time, but that's it for today. So